Today we're going to pick up with our study of kinetics, and we're moving into second order kinetics. And so, as we saw when we did first order, the formula for the integrated rate law is on your formula sheet. It is the second equation shown on the sheet, and so you've got first order and then second order, so they are in order. And if we look to see kind of how it varies from what we saw with the first order, instead of seeing any natural logs, we see 1 over concentrations. So again, if we look at this in the form, because this form is a little different than what you're going to see on your formula sheet, but the reason is you can kind of see what the linear is going to look like. In terms of y is equal to mx plus b, our y is going to be 1 over the concentration. So when we look at that y-axis, you'll see 1 over concentration. And then our x is still our t, so it's going to be versus time. And so with second order kinetics, you would see a straight line when 1 over concentration versus time is plotted. So that's kind of your key to say, oh, if that's what they've plotted and they've gotten a straight line, then that is second order. Again, your y-intercept is a function of a naught, but this time it's 1 over a naught. So if you have your y-intercept equals 1 over a naught, then we know in order to solve for what a naught would be, you can plug in the y-intercept and take the inverse of it. So the half-life for a second order reaction is not given on your formula sheet, and that's a clue to you that it wouldn't be asked of you on the AP exam. So if we look at it, it looks a little different than what we saw for first order. Remember, for first order, T1/2 is equal to 0.693 over K, and it only depended on the rate constant, which meant the concentration didn't matter. Your half-life would always be the same. When we look at second order kinetics, the half-life does depend on the starting amount. So it's still K in the denominator. The 0.693 is replaced with a 1, and we've got the product of both K and the starting concentration. So the question asks, how does the half-life of a second order reaction compare with the first order? Well, the main differences are the 0.693 is switched out for a 1, and then the denominator includes a naught, which tells you that the half-life is changeable. So depending on the initial concentration, the half-life will change. And that's not something we're used to, because in first year, when we did radioactive decay, it was always constant. The half-life didn't change. But that was because it's a first-order kinetic situation, and we do have things other than first order. All right, so if we go into practice 9, it says the differential rate law for the reaction of iodine atoms to molecular iodine is given. So the rate is given as K times the concentration of I squared, and they give you the value of K. So right away, since we've seen the differential rate law and we see that the exponent is a 2, we know that this is a second order reaction. So A says, based on the differential rate law given, the formation of I2 is, so what we just said, second order with respect to I. This means if the concentration of I is doubled, the rate of formation of I2 would. So if we double this and we square it, it would go up by a factor of 4, or quadruple. So then they gave us the value of K, but they certainly didn't give us the units. And so they asked, well, what are the appropriate units for K? So remember that it's always inverse molarity, and then time in the denominator, and it's to 1 less than the order. So inverse molarity would be liters per mole, both raised to the 1, because that's 1 less than 2, and then times seconds or some other time. They want us to write out the integrated rate law, and again, if you are unfamiliar with kinetics, you might think, how in the world am I supposed to do that? But if we know that the differential is saying it's second order, then we can go to our formula sheet, and we know that second order kinetics is 1 over the concentration. So we come to write out our integrated in terms of I. We would say 1 over the concentration of I equals K, which they gave me, 7.0 times 10 to the 9th, times T plus 1 over the starting concentration. And they didn't give us starting concentration anywhere that I see, and so we wouldn't actually have anything to plug in there. We would just leave it in there symbolically. So in part D and E, they give you some more information and ask you to solve. So they say if the initial concentration is 0.4, calculate I after this many seconds. So again, if we want, or using time, we have to use that integrated rate law. So 1 over concentration of I equals 7.0 times 10 to the 9th times time, so 2.5 times 10 to the negative 7, plus 1 over the concentration of 0.40. So if you want to pause the screencast and go ahead and work that out, make sure you can get the answer mathematically, because 1 over the concentration is going to be equal to this number. So you need to think about mathematically what you have to do to actually solve for I. Okay, so hopefully you got that I concentration was 5.7 times 10 to the negative 4. If you didn't, please go back and figure out where you might have gone wrong with the algebra. So in part E, they tell you, again, the starting concentration is still 0.4. What is the half-life for this reaction? All right, well, we just saw that half-life for a second-order reaction is 1 over K times the concentration of A naught. So we've been given K up here. They've given me A naught, so it's just a matter of plugging in 1 over K. So K is 7.0 times 10 to the positive 9th times 0.40. And when you do the math, that comes out to 3.6 times 10 to the negative 10th seconds. All right, moving on to practice 10. It says a certain reaction has the general form A forming B. At a particular temperature, A naught is given. Concentration versus time data were collected for this reaction, and a plot of 1 over A versus time resulted in a straight line. Again, if you're looking at that and you're not familiar with kinetics, you're kind of like, so what? But what they've told you is that when they plotted 1 over A on the Y and time on the X, they got a straight line, and then the value of K, or actually the value of the slope, is equal to 3.6 times 10 to the negative 2. So if I think about my second order kinetics, 1 over the concentration of A equals KT plus 1 over the initial concentration of A. What we said was important about slope is that we can get K from it, because T is our X, so K is our slope. And again, the safest thing to say is that the absolute value of the slope is equal to K, because in some of the integrated rate laws, K is negative, in others it's positive. So you cover your bases if you just say take the absolute value of the slope, and that's going to be equal to K. Well, they've literally told you what it is. Now they also gave you units, which is kind of nice, because even from the units we could have figured out that this was second order kinetics. Alright, so in A they want us to determine the rate law, the integrated rate law, and the value of the rate constant. Let's do the easiest one first. The value of the rate constant, right, if we understand kinetics, comes from the slope, so K is just equal to the 3.60 times 10 to the negative 2. For the rate law, if this follows second order kinetics, then I can say rate equals K times the concentration of A, and my exponent is 2 because it's second order. To get my integrated rate law, if it's second order kinetics, I know it's 1 over the concentration of A equals K, which is 3.6 times 10 to the negative 2, times T plus 1 over 2.80 times 10 to the negative 3rd. Now, if you're asked to do anything mathematically with this integrated rate law later, I would certainly go ahead and solve for this, but like if it's the AP exam and you're doing an FRQ, this is totally acceptable to leave it in this form. I know your math teacher would hate it, but that's totally fine because you are showing the chemistry. Alright, in part B they want us to calculate half-life, and we know that if it's second order, it depends on both K and A naught. So we've got 1 over 3.6 times 10 to the negative 2 times 2.8 times 10 to the negative 3. When I work that out, K comes out to 9,920 seconds, or about 2.8 hours. Alright, in part C, how much time is required for the concentration of A to decrease? So again, we've got these two rates. Which one is more useful if they're asking about time? So the integrated rate law is what we would want to apply. So we're going to use that down here. They want the concentration to decrease to this. So now we know a certain concentration. So 1 over 7.0 times 10 to the negative 4th equals, my K is 3.6 times 10 to the negative 2. I'm solving for T, and then I have plus 1 over A naught. So 2.8 times 10 to the negative third. This is what I was saying would be easier to go ahead and solve since we're actually having to use it now. And again, remember, this is also the inverse. So get a number, bring this over, and then divide by that k to solve for t. And we get 2.98 times 10 to the 4th seconds, or about 8.27 hours. All right, so that's our second order kinetics. The last we're going to talk about is zero order. It's popped up on the AP exam. Since it's not on the formula sheet, when it has popped up, they have given you the integrated rate law when you needed it. Different ways they could tell you that it's zero order. They could say things like, you know, it was a one reactant system and we doubled it and nothing happened to the concentration. So, or sorry, nothing happened to the rate. So that tells you they're changing the concentration but nothing's happening. So that is zero order kinetics. It's certainly simplified when we look at zero order. If we look at y is equal to mx plus b, we don't have any natural logs or inverses. Our y is just the concentration. Our x is our time. And again, the negative pops back and we've got a negative k. So the absolute value of the slope is equal to our k. And our y-intercept is just equal to the A naught, or the starting concentration. So the moral of that story, if you graph the concentration of A versus time and you get a straight line, then you know it's zero order kinetics. The half-life, this I've actually not seen on the AP exam, but it is given to you. The half-life is the concentration of A over 2 times the rate constant. So it does depend on both the K and the concentration of A. All right, so we have additional practice problems. So we're adding this in to our first order. So if you've got your textbook handy, I'd like for you to look at an example kind of where we're heading. So if you look at example 35 in your book on page 601, you know, when we did first order kinetics, you knew that all those homework problems were going to be first order. So you really didn't have to do anything graphically. So there's a couple different ways your textbook will set these up. So if you look at 35, they've given you these 3 graphs. And so if you look at the 3 graphs, you're like, well, I see a curve, and a straight line. And hopefully you picked up on the fact that straight lines are important. So when you look at 35, if they've already done the work for you and graphed these, this is great. You find the straight line, and then your eyes need to immediately go to that y-axis. So when I look at 35, the graph on the bottom is the one that gives me the straight line. I look at the y-axis and I see it's 1 over the concentration of A. That tells me that this system is second order. That means I can immediately write my rate law, and that means that I can immediately use the integrated rate law, 1 over the concentration, blah, blah, blah. Now, as for slope, you would, you could certainly pick a point and solve, because that's a pretty nice linear fit. So you could certainly pick a point. You could pick 2 points and calculate the slope and find k. Or you could pick 2 points that aren't on the line to find k. So there's several different ways you can find k, but because of that, when we go through homework, your answer to k may be a little bit different. All right, so that's kind of the easiest, is when they give you the 3 graphs. Okay, so if you're working on a problem, let's say like 33, you've got this table of time versus concentration. They tell you that they studied it, and they tell you, this kind of generic rate, which is not an integrated or a differential. So your plan of attack for a question like 33 is you have to plot all 3 possibilities. You've got to plot the natural log of concentration versus time. You have to plot 1 over concentration versus time. And then you have to plot just concentration versus time. Look at your 3 graphs and see which one gives you the straight line, because that tells you if it's 0, first, or second order. So hopefully that makes sense, and that gives you kind of some tips heading into your homework. But please know that you can't just use time and concentration data that's in a table to figure these out. You have to graph and apply. So whether you want to do that in Excel, it's totally fine, or in your graphing calculator, it needs to be graphed. And so you've got to write in, some evidence of what you have done to figure out what order the reaction is.